Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let's get started. Many thanks to Pratik and the organizers for putting up a fantastic program, and thanks to all of you for coming to this penultimate session of the workshop. I'm going to talk about a slightly different application from what you've seen in the past 4 to 5 days, and that's program verifications. How do you check the reliability of programs using machine learning techniques? I'm going to take a machine learning perspective to testing the quality of programs, in particular the correctness of programs. We design software with the hope that it satisfies end user requirements such as end user functionality, no security bugs, high performance, doesn't crash, and so on and so forth. And the fundamental question in everybody's minds, that is developers, users, and testers, is that does the software really work? And one popular approach, at least adopted in the industry for checking the validation of software, is testing. It's the old-fashioned way. You basically run your software for some time and see if it works. If it works, then you're good to go and you're good to ship. If it doesn't work, you fix the bugs, and that's just about it. So that's the state of the art in terms of reliability of software. Of course, I'm sort of simplifying the problem here. There are sophisticated ways of testing, but all these approaches typically just run the software in a variety of ways to check if there are bugs. So what's wrong with testing? So here's an excerpt from Dijkstra's Turing Award lecture called The Humble Programmer, where he says that program testing can be a very effective way to show the presence of bugs, but is hopelessly inadequate for showing their absence. And essentially what Dijkstra is saying over here is that even after you execute the program many times, we still don't know if there's another test which can actually exhibit or cause a failure. So that leads to the motivation for even doing program verification, and program verification is defined to be the algorithmic discovery of properties of a program by inspection of the program source text. So you don't run the program, you just like a compiler, you sort of look at the source of the program text and try to establish correctness of the program. This also goes under many names: static analysis, static program analysis, and formal methods. Right, so what's the problem? So you're given a sequential program written in C, C#, Java, your favorite programming language, with input I, and you're also given an assertion which is the property that you want to check. And I'll make this very clear with an example a little bit. And the two questions we want to ask: is there a bug? That is does there exist an execution of the program for which the assertion is violated? Or we want to know whether the program is correct. Does the assertion hold for all possible inputs to the program? Right, so here's an example. I have a program here where you have two variables x and y, both initialized to 0, and then I have a loop which is a non-deterministic loop where the star just denotes a condition that is dependent on the inputs, and inside the loop I increment both x and y, and then I have another loop which decrements x and y while x is not equal to 0, and over here on line number 6 I want to assert that the value of y is 0, and the question is the value of y 0 for all inputs to the program? So let me give you an oversimplified version of how people actually do program verification for this particular example. So like I mentioned, the objective here is to come up with a proof that says that the value of y at this program point at line number 6 is indeed 0. And the way they do that is to model the program perhaps as a state transition diagram where every statement of the program defines the transition relation. So let me simulate that for you. So let's assume that just before statement number 2 you know that x equals y, and that's indeed true, right? So after executing the statement x equals y equals 0, the fact that you know about the program is that before you execute line number 2, which is pc equals 2, the formula x equals y holds. And then when I enter the loop at statement number 3, I know that the formula x equals y still holds. And when I exit the loop, well, I still know that x equals y holds. And let me enter the next loop, which is while x not equal to 0. when I enter the loop, I know that x equals y, and when I exit the loop, I know that, well, at line number 6, you know that x equals 0 and y equals 0. And with this formula, it is possible, it is obvious that at line number 6, y equals 0. Right? So what I've done is that somehow, using some analysis, I have pushed through formally through the program without actually executing it. And I've established a formula before the assertion which implies that the assertion holds. And these formulas that I've got over here are known as program invariants. So they're formulas which are true for all executions of the program. So if I were to pick any of these formulas and take any execution of the program, then that execution would indeed satisfy each of these formulas. So the whole key problem in program verification is to compute these formulas or invariants. And that's precisely what I'm going to talk about in this talk. How to use machine learning techniques to figure out what these invariants are. Right? So the question is, can we guess an invariant from good and bad program states for the purpose of program verification? And the good states here are program states or executions which do not lead to a violation of the assertion. The bad program states are program states which represent a violation of the assertion. So for example, in this program, at this program point, a value of y equals to 4 is a bad program state. And a value of x equals y equals 0 at this program point is a good program state. So is this clear? Right. And essentially what I'm going to do is I'm going to use...
So, but a buggy program will not have the invariants that you want. So
a buggy program will not satisfy the invariants, that's right.
But you will be able to see only a buggy program, right? So how will you figure out that this is the invariant that I want?
So I'm given a program, and upfront I don't even know whether the program is correct or incorrect. If the program is correct, I want to establish an invariant. If the program is incorrect, then I want to basically give a proof that the invariant is violated, and that's a bug.
No, but how would you know that what is the true or correct invariant for you?
What is the true or correct invariant for you, Vinny?
He has the invariant before he starts. He knows what our desired output is.
So the
Invariant beforehand.
Oh, no. So I have an objective, right? I have a program, I have an assertion, right? I want to basically check whether the program satisfies the assertion. That's my objective. If it satisfies the assertion, then I will want to get necessary invariants which will prove that the assertion holds. If the assertion is violated, then I want to get necessary violations of the invariant which basically prove that the assertion doesn't hold. Both. Right, and here the whole objective is to, so since this is based on, the earlier example I showed you, the symbolic simulation and so on was based on symbolic evaluation of the program. It's based on actually making queries to many NP-hard questions in the approximate world. And furthermore, something I should have mentioned, the general problem of assertion checking is undecidable. So what we want to do in the practical setting is, even though it's undecidable, there are buggy programs and there are correct programs, and the problem doesn't go away. And we still want to build tools which, to the best of our abilities, can either find bugs or find proofs. Right? And one nice thing about the approach which I'm going to describe to you is that we were able to efficiently compute invariants or proofs or a variety of challenging benchmarks that occur in the programming languages literature. Right? So let me focus on a particular type of invariant. So let me focus on a particular type of formula which is called an interpolant. So question? Interpolant. Interpolant. Yeah. So interpolant for a pair of formulas. So I'm given two formulas A and B, and I know that A and B is unsatisfiable. Right? So I feed A and B to a SAT solver and it says unsatisfiable. So the interpolant is a formula I such that A implies I, that is the set of all satisfying assignments of I is a superset of the set of satisfying assignments of A. And then I and B is unsatisfiable, that is the intersection of the set of satisfying assignments of B and I is empty. And then there is a small technical condition which basically says that the variables that participate in the interpolant are a subset of the intersection of variables in the formula A and the formula B. Right? And this is a sort of a subclass of possible invariants, and they're very useful because they usually result in very nice parsimonious or simple proofs. So one thing that we are concerned about in our area is that when you, not only do we want to compute a proof, we want to compute a beautiful proof, and these interpolants are used for computing these beautiful proofs. aesthetically pleasing proofs, so to speak. They don't really look beautiful. So here's an example. Suppose I have a formula A, which is x is greater than or equal to y, and a formula B, which is y is greater than or equal to x plus 1. Then the formula 2x plus 1 is greater than or equal to 2y is one interpolant. And let's see why this is so with the help of this diagram. So here I have, let me look at things in the xy plane. I have this blue area, which is x is greater than or equal to y, and then I have this red area, which is y is greater than or equal to y plus 1. And this line over here is the line 2x plus 1 equals 2. And this region over here is the interpolant. So essentially, right, what I'm trying to say over here is that this interpolant in some sense separates A from B. So it separates the formula A from B, and that's precisely the connection that I want to draw to well-known problems in machine learning. Right. So here's a problem most of you, in fact all of you, are very familiar with, which is binary classification. So I'm just switching gears here because I quickly want to draw the connection between computing interpolants and binary classification. So I'm given points with labels +1 and -1, and I want to find a classifier which is a map from points to true and false, such that all positive points get the value true and negative labels get the value false. So what's the connection? So essentially we've seen that from the diagram that an interpolant separates the formula A from the formula B. And in classification we have a separator which separates positive examples from negative examples. So the first question we asked ourselves is there a connection? And fortunately for us the answer is yes. So the main result that I'm going to show you is that we can look upon these invariants or interpolants as classifiers which distinguish positive examples from negative examples, and I'll say what these positive and negative examples are in a little bit. And we use SVMs for this purpose. And there's also a nice connection between the fact that SVMs are predictive versus the whole objective of obtaining generalized predicates for verification. And I'll say what a generalized predicate is in fact right now. So the standard mantra for computing these invariants, and things get really tricky when you have programs with loops, because if you have a loop-free program, you can take that program and systematically transform that to a formula and feed it to a automatic theorem prover, which is a logical inference engine. And if the logical inference engine says yes, then you know that the program is correct, and if it says no, then the program is incorrect. On the other hand, if you have a program with unbounded loops, then it's not clear as to how one does this translation, because then you would get an unbounded formula. And the whole point of the invariant is to sort of summarize that formula in a succinct and compact manner. So you can sort of look upon an invariant as a predicate which denotes a fixed point of the reachable state space of a program. So you can actually take a program and convert it again into a finite formula, even though the program represents an infinite or unbounded state space. So
you showed this, the way to think of an interpolant is something that separates A and the formula A and the formula B.
Right.
So what is the space in which this separation is being achieved? Is it the space of all possible inputs?
Yes, it's the space of all possible inputs.
Variables that A takes in from variables, that defines the feature space, and then the values of those variables.
Right. And in particular, that's a good point. So in particular, it's of course in the space of all possible inputs, but it's also I'm looking at these predicates or these A and B's, these formulas at one particular program point. So I basically say let me focus at onto one program point, and then look at all those states which satisfy A and satisfy B, and then compute these separators. So
you get the a formula can be sort of thought as at least is sort of some sort of, let's say, polytope,
right,
a convex formula,
half space in our case, yeah.
So do you get samples from that body, or
oh, good point. So that's what I'm going to show you. So and that will become clear in a little bit. So essentially when you do program verification, I mean, since we need to sort of somehow argue in a formal way about a potentially infinite state space program, what people normally do is take this program which represents an infinite state space, and this happens if you have loops and so on, unroll the loop some fixed number of times, then compute a candidate invariant which represents a superset of states for that unrolling of the loop, and then hope that unrolling, that this invariant that you computed with a finite number of unrollings generalizes to the actual program. So that's what they do. Right? So that's precisely what I've written over here. So you unroll the loop, find your invariants or interpolants, then hope that it generalizes to an actual proof or an invariant. And this is analogous to what you guys do with SVMs as well, right? Or classifiers. You have a training set, you compute a classifier, and then you hope and pray that it generalizes to things in the test set, right? So this seems, and which also means, it seems to suggest that in both cases, right, you need these classifiers as well as invariants to be predictive. So in the case of program verification, the invariant that you compute for a fixed unrolling of the loop needs to generalize or have the predictive power of what might happen at n tends to 10,000 or whatever, whichever n is the number of iterations of the loop, and likewise for SVM for a classifier as well. So these are slides I have usually for a PL audience, but so the point is to basically say that we use SVMs to compute these classifiers, and essentially all the separators that you obtain. So the point of this slide is to say that once you have positive examples and negative examples, it turns out, and I'll show you this in a little bit, that all separators that we obtain are good interpolants. So they're all.
The cost is to see if there is even one separator that will completely separate, or
right.
do you want the max margin? Is that important?
Good question. So in our experiments, the max margin one is a good one, and I don't know why. So, but we can discuss that a little later. So let's look at the same example. And like I've said, you have this program and it has two loops, and if you want to sort of employ symbolic execution or symbolic simulation, we need to convert this into a finite program, that is a program with a bounded number of loops or fixed length. So what I'm going to do is to unroll both the loops once. The first loop is unrolled once, and that's modeled with this if statement, and the second loop also is unrolled once, and that's also modeled with this if statement. And essentially what this is saying is that if I unroll the first loop once, I increment x and y once. If I unroll the second loop once, I decrement x and y once. And let's also assume that we're interested in computing the invariant, that is a predicate which represents a superset of all program states that can occur at statement number 4. Right? So what people do, and I'll brush the details under the carpet, is that get the formula corresponding to statements 1, 2, and 3, right? And you'll have to believe me that is this formula over here, and I'll call it A, right? And then get the formula which corresponds to 5, 6, 7 and the violation of the assertion, right? And let that be the formula B, right? And if you just take these formulae and feed it to a logical inference engine, it will tell you that A and B is unsatisfiable, right? So that meets the first condition for an interpolant. All it's saying is that this program is a correct program because it's a finite program. And furthermore, the interpolation procedure will actually tell you that the interpolant or the invariant is x equals y, and that's pretty obvious from this program, right? So you start off with x equals y equals 0, increment both x and y once, and then decrement x and y once, and you can see that every program point you've established the fact that, or the formula that x equals y, and then you just go back to the original program and then ask, oh, is x equal to y an invariant? And it turns out that it is indeed an invariant, because even if you were to execute the loops, the first loop 1,000 times and the second loop 1,000 times, you still have this formula at every program point which is x equals y that holds, and that's an invariant.
Well, here, how do you know this magical thing about unrolling each loop the same number?
So good point. So essentially, that's why I said don't worry about how you got the formula. So people are going to sort of do some logical inference techniques to figure out various other things. But all I wanted to sort of say is that, well, I've unrolled the loop some number of times and then figure out an invariant. And for this particular example, it turns out that that invariant that I've computed for the bounded program is also an invariant for the unbounded program.
There is one bit of danger here, because when you are unrolling the loop, your next point is dependent on your past point. So
right.
These typical conditions of IID is like terribly violated.
Oh yeah, absolutely. Yeah. Right. Yeah, I know what your worry is. I mean, if I were to use SVMs in a blind manner, then things can go wrong, right? But I'm going to do something slightly smarter. So let's see. Right. So let's see how you might want to solve this using a machine learning approach, right? So I'm going to take, like Prateek pointed out, I mean, I have these two formulae, and he suggested that I might want to sample from both A and B, and of course there might be other problems like independence and so on, but I'm not going to worry about that as yet. So I'm going to take A and B. I know that A and B is unsat, and what I'm going to do is sample maybe the points 1, 1 and 0, 0 from A, and sample some other negative point from B. So my samples from A are the positive examples, sample from B is a negative example. Then I'm going to get a separator using an SVM, and using the separator, the half space that contains my positive examples, I'm going to basically say that that's my interpolant. So in this case, it turns out that the interpolant that I want is 2y is less than or equal to 2x plus 1. Right? So this is the general idea which I'm going to use, and it has problems. So and we'll see what these are. Right. So up to now are things clear? So the whole problem setup. So essentially, what I'm going to do is that I'm going to do a little bit of program analysis to get these formulae A and B, and then step away and use maybe some data-driven techniques like SVMs or classifiers to compute these invariants. That's the general plan at this point. Arun?
How do you get the negative sample?
I sampled from B.
What do you mean by you sample from B?
So I got a satisfying assignment from B. Right. So remember that A in this program was the formula obtained by, this is the formula which represents 1, 2 and 3, and B was the formula which was 5, 6, 7 and y not equal to 0. Right. So that's what I did. So
sample from B means that you might, at a different run of the program, you would have unrolled the loop twice, and then.
No. So right now I'm starting off at this point where I have these formulae A and B.
Right.
So I'm just going to ask a logical inference engine, give me some satisfying assignment to A, right? And then I'm going to ask the engine, give me some satisfying assignment to B. So A are all the examples from A are positive examples, and all the examples from B are negative examples.
What is the cost of doing this sampling?
It's NPR. But the problem is undecidable, right? So I'm sort of doing things very, very efficiently here.
Can I just keep on getting more and more and more training data? Like, can you keep feeding me an infinite amount of data if I want?
Yeah, I can.
Not at very much cost.
NP hard cost. By no means am I going to do polynomial time things here.
Oh.
Yeah. But what we find is that we built these class of theorem provers known as SMT solvers, which are satisfiability modulo theory solvers, which are which work very well in practice. So that's what most program verification engines are based on. So for example, that's what Yogi is built on, and it scales to large programs. Right. So here's the vanilla algorithm, which I'm going to call basic. So what I'm going to do is, and of course, as you've seen, you have two formulas as input, A and B, and the first condition of the interpolant basically says that I'm only interested in computing an interpolant which is defined over the common variables of A and B. So let that set of common variables be vars, and this first statement, add samples to x plus, is basically saying sample the satisfying assignments of A and assign them to sample the satisfying assignments of A and assign them to and project them onto vars and put them into a set x plus. Those are your positive examples. Likewise, sample from B and get your negative examples. Use an SVM between the x pluses and x minuses to get a separator, and using the separator and the set of positive examples, get this half space, like the one you saw in the earlier example, and that's your candidate invariant. So the half space is the half space containing the set of all positive examples, and that's your candidate invariant. And as many of you have noticed, there are problems with this algorithm. First of all, the samples that I have drawn might not be linearly separable. So I might get samples like this, plus plus, circle circle, and until now I've been assuming that there's this nice linear separator which is going to separate the positive examples from the negative examples. So that's one problem. And the other problem is something Pratik pointed out, is that I'm sampling from these formulas, right? I want to actually compute a separator between A and B. But what I've been doing thus far is to sample from A, sample from B, which are subsets of the set of all satisfying assignments to A and B, and claiming that could be an invariant or an interpolant. So it's quite possible that the invariant or interpolant I compute from the samples might not actually be the separator for the formula. So there are two problems here. So what do I do? So let's quickly see what we do if there is no separating inequality of half space. So until now I've been assuming that there's this nice half space which separates the positive examples from the negative examples. So what I'm going to do is something very simple. I'm going to iterate over the set of all negative examples, compute the half space corresponding. So for each negative example, compute the half space that separates that negative example from all the positive example, and take a conjunction of all those half spaces. Right? So this is like learning an intersection of half spaces is what we're doing. So just to illustrate this, so for these two examples, I learn this separator and there's a half space corresponding to that. And next, for this example, this is the separator, and the intersection of half spaces is exactly this guy. And this represents the predicate 2y is less than or equal to 2x plus 1 and 2y is greater than or equal to 2x minus 1. And that's an interpolant separating these x pluses and x minuses for this example.
So why not something like decision? Because they also have nice formula kind of.
Right. So one thing that I don't know much about this, but one thing which we really wanted is that we wanted a classifier which does not misclassify on training examples, because that is required to basically get progress guarantees and so on. So that's the reason why we chose SVMs to start with.
You also want to that if you grow your decision tree down to if there's only one point in a leaf node. I
see. So I don't know much about this, and maybe I should talk to you later. Yeah. So, but the point is that since we're doing program correctness, right, we have to be very careful about what we output. When we say yes, right, it better be yes. I don't want to make statements like, well, let's see, by and large, yes, and the rest of it, figure it out, and so on. I need a formal proof to say that the program indeed satisfies the assertion, and that's what we're aiming for. So, in any case, at this point, it seems like we partially solved the linear separability problem by saying that I'm going to give you a more expressive interpolant or invariant, which could be a conjunction of half spaces, right? And that seems to suffice for a number of programs. But what if, so the next problem is, of course, that the candidate is not an interpolant. So I've drawn some positive examples, negative examples from these formulae, and then I have a separator which is not a separator for the actual formula. There could be other positive examples and other negative examples which I've not as yet seen, which might actually spoil things for me. So here's a procedure which I'm going to call interpolant A and B, which works as follows. So it's going to first have a random set of positive and negative examples, which I'll denote by x plus and x minus, and it's going to do the following in an iterative manner. So first what it's going to do is it's going to call the procedure that you saw earlier, which is going to learn the intersection of half spaces on the current set of positive and negative examples, and I'm going to call that intersection H, and that's the step which finds me the candidate interpolant. And then recall that there were three criteria for an interpolant. One was that the interpolant only had variables which are common to A and B, where A and B was the input to the procedure, and the other one was that A implies I, right? So the satisfying assignments to I are a superset of the satisfying assignments to A, and what we do is we just check satisfiability of this formula, which is A implies I, right? And we again feed this to a SAT solver, and if the SAT solver says yes, then we're in good shape because one of the conditions is satisfied. If not, we use the reason for unsatisfiability to add more examples to the positive examples. So essentially, once the SAT solver basically says that A implies I does not hold, then typically what we get back is something known as an unsat core, which is a reason for unsatisfiability, and we can sample from that unsat core to add more examples to our x pluses, or the positive examples. Likewise, the second condition is that I does not intersect the set of bad states, and if this condition is not satisfied, then again we get the reason for unsatisfiability and take all the examples which are reasons for unsatisfiability and add them to the set of negative examples. If both of these conditions are satisfied, it means we have an interpolant and we exit. Otherwise, we keep doing this until we get an interpolant. So this is a sound yet incomplete procedure in the sense that there's no guarantee for termination here, but if it does terminate, what we're able to show is that we actually compute an interpolant. Right. So let's see how this works over our running example. So I sample from A and I get these two positive examples and one negative example, use the SVM and get one half space, and then first ask the question, is this candidate interpolant, does this candidate interpolant satisfy the formula A implies I? And it does satisfy the formula A implies I. And the next question I ask is, well, does this interpolant satisfy the formula I and B is unsat? And in this case it doesn't satisfy it, and the reason for unsatisfiability is this negative example over here. So I add this and then again ask the SVM the conjunction of half spaces, another question, and I get this separator, and it turns out that this is the interpolant that I want. Okay. Right. there are also other advantages to this so-called sampling procedure, where people write really crazy programs, and our state of the art in terms of program analysis is not quite there. So for example, if I were to take this example where you have lots of nonlinearities, so I have a program here foo, which first takes an input z, and then x is a function of sine z and y is a nonlinear function of cos z, and then I want to assert that x is not equal to 2 or y is equal to 2. And this is a program, even though it looks simple and small, a program that no existing program analysis tool can handle. And essentially what we do is we basically again compute these the formula representing positive examples and the formula representing negative examples, and in this case it turns out to be this formula A over here, which is x1 equals sine squared z and y equals cos squared z, and B is the negation of the assertion, which is x equals 2 and y not equal to 2. And we use the same approach, and then we compute an interpolant which is x plus y equals 4, which is a linear separator. And using this you can actually show that this program is correct. So there are lots of advantages to doing this taking this so-called data-driven approach, because it sort of removes superficial nonlinearities. So since I don't have too much time, the whole point of I don't want to get into the details, because the whole point of this slide is to say that we work reasonably well. In fact, the results are quite promising. There are nitty-gritty details with respect to logical formulae and so on, which I won't get into. But the upshot, what I want to basically say is that it works on many examples which are challenging benchmarks written by people in the programming languages community. Right. So as some of you might have noticed, I only talked about computing invariants, which are conjunctions of half spaces. But in general, right, you could imagine proofs which have arbitrary combinations of half spaces. Right? What do you do over there? So more recently, we've been looking at guessing these candidate invariants using pack learning techniques, where we want to compute likely invariants. And Nanik shakes his head here.
You want to look at multiple kernel.
Yeah, teach me some things, and I'll apply other things as well. But essentially, with pack learning, we basically just used standard algorithms, and in fact, some of them were pointed to us by Pratik, where we discover. So the complexity of discovering invariants, even if you're given the set of base invariants, is actually NP to the NP, whereas we can actually, by introducing some error, we can actually discover likely invariants in polynomial time using pack learning techniques, and we have a paper submission which does this. And we also have SVD techniques for discovering polynomial invariants. We also have similar techniques for checking for program termination and so on and so forth. And if you guys have other ideas as to how we can do this, I'll be happy to learn these techniques from you. And right after this talk, I'm going to talk to Manik, of course. So to quickly conclude, well, we've barely scratched the surface in terms of showing that classification-based algorithms can be used for computing proofs in program verification. And we've done a lot of follow-up work on using techniques from linear algebra and pack learning for scalable proofs. And this is something I like to call as data-driven program analysis, where the whole objective is to take a program, systematically convert it into data, and then use powerful data processing techniques, because they are really because data processing techniques have a lot of scalability to offer, whereas existing program analysis techniques do not scale to large programs. And in particular about these, the details of the SVM work appears as a paper in this conference called Computer-Aided Verification, and it's available on our webpage. So thank you, I'll be happy to take questions. Yeah, Manik.
So I got very confused by this thing about generalization and overfitting. So you say you want to classify all your training data correctly, but you want to generalize well, and how do you choose the number of half planes you will fit and things like that?
How do you choose the number of half spaces, is it?
Yeah, I mean, first just the generalization versus overfitting. What exactly do you want to do?
So essentially, in terms of generalization, all that I was trying to say was that when you do program analysis, you can look upon this bounded program that you look at as your so-called training set, compute whatever you can from that program, and then hope that it generalizes to the whole program, which is an unbounded beast. Right? So likewise, when I sample from my formulae A and B, I'm looking at a subset of the potential number of subset of the potential space of satisfying assignments of both these formulae. Then I compute this interpolant, and then again I use a logical inference technique to check whether I've actually generalized sufficiently to the actual invariant. I don't know whether I'm making sense here, but I should.
So one thing maybe that if you use, so I think Manik is worried about you might use too many half spaces. And yeah.
I might use too many half spaces. Okay, I see.
The bad point to that is that his interpolant will look very ugly. It won't be aesthetically pleasing.
Right. So good point, right? So there are two problems here. One is that you'll get a simple proof, or you might get a ugly duckling, but we don't care. We get a proof because first order of priority is to get a proof. The second is beauty. But to be honest, I don't know how to sort of at this point get a beautiful proof, even if there existed one. So that's an interesting question. So if I want to sort of minimize the number of half spaces, for example, that I'm going to use. Yeah, tell me. So yeah.
Only one answer in the world, whatever the question is.
Excellent. So I don't even know the answer. So yeah. Yeah, question.
In an experiment, is there an example where this failed?
No.
It will not fail because you're anyway trying.
No. So actually, good point. Right? I should correct myself. So we took all these. We took all the challenging benchmarks where the invariants were known to be conjunction of half spaces, and we discovered all of them. But if I take, there are other benchmarks where the invariants are an arbitrary combination of linear inequalities, and then we would fail. Right. So.
Is there any way you can generate data from running the program?
Yeah. So the other paper which uses pack learning, which Manik doesn't like, generates runs the program. So yeah, because that's a natural way to do it. But running the program is a nice way to generate good states.
Yeah.
The hard part is how do you get the bad states, right? Because if you already know what the bad states are, you're done. I mean, you've done the job already. So that's the hard part. Yeah.